Buenos dias. Me llamo Ravi. And that's the extent of Spanish my kids have taught me so far. So the rest of the talk will be in English, but I look forward to learning it more for the duration that I'm here. My name is Ravi Rao. I'm accompanied by Charlie Wen. We're both program managers on the Windows Core Networking team. And today we're going to talk about what are the new things we've built in Windows Server 2012 R2. This event is happening in Europe. The picture seems to say it's in North America, but it's actually happening in Europe. The agenda that I'm going to be following is, in general, I'll talk about where we are coming from, what we did in 2012, where we're going in 2012 R2, and focus most of the discussion on three broad areas. So the bulk of the time I'll be spending will be on the first area, cloud scale performance and diagnosability. I'll then go and talk about the comprehensive inbox SDN solution that is partner enhanced. And I'll spend very little time on core infrastructure enhancements because there is a deep dive session that is already set up for it. So we made great strides in 2012. In 2012, one of the big things we did was to refocus the company on the cloud. And born out of that was the Cloud OS vision, a vision whose goal was to provide unparalleled flexibility in deployment and management of workloads across all clouds. So the clouds could be the customer cloud, it could be a service provider cloud, or it could be an Azure cloud. And the bedrock or the foundation in order to enable these workloads to be placed in any cloud based on customer demand is networking. And so networking was a big focus area in the Windows Server 2012 timeframe to enable the Cloud OS vision as we had laid it out. And so in 2012, we invested across a broad set of areas. We invested in continuous application availability. How many of you are familiar with NIC teaming that was done in 2012? A lot of folks. It was a very, very popular feature that we invested in the 2012 timeframe. We invested in SMB 3.0, multi-channel, and a suite of other investments in that area. We built out a richer ecosystem around the platform capabilities we had to give you more choice. How many folks are familiar with the Hyper-V switch and the ecosystem surrounding it? You know, we built a multi-tenant infrastructure to enable the clouds of the future. So not only did that mean we supported PVLANs and other similar capabilities, but we also supported new technologies. We invented new technology, one of them being the Hyper-V network virtualization, which I'll talk about briefly today. In the cloud, one of the things that's most important is performance. Cloud scale performance is critical, and so we invested in a suite of features to enhance performance of Windows Server 2012 with RSS and VMQ and SRIOV. You know, there was a range of technologies that we built to allow VMs to get as much performance as they possibly can on the machine that they were hosted on. And finally, we had a set of core infrastructure and automation-related enhancements with a large number of PowerShell scripts that we built in 2012, System Center VMM, and then areas such as branch cache and direct access. So this was the 2012 wave, a wave that was intended to allow us to set up a foundation for us to look forward and invest into the future. Now, once we shipped 2012, we did a couple of things. We talked to a lot of customers about the challenges they have based on what we had already shipped. And then we peered inside our own data centers. So we run some of the biggest data centers in the world with Windows Azure and Bing and Office 365. And the idea was to look into the set of things that these data centers care about based on the deployment experience of Windows Server 2012 itself. And some, let's call it obvious in some cases, things came out. The first thing is that costs matter. Cutting costs is important. And the mechanism that these data centers use for cutting costs is not necessarily to buy bad equipment. It is more to maximize the return on investment on the investment that they have already made. So if I have, a 16 core machine, I want to be sure that I'm using every single core on that machine. Maximize capacity. If I have a 10 gig network interface card or a NIC, I want to be sure that I'm maximizing utilization of that NIC to the extent possible. And to do so, ideally on commodity equipment. That is, you're not having to go and buy a lot of specialized equipment to get these kinds of performance gains that you're looking for. You can do that based on commodity equipment that is available in the market. So that's the mechanism that was being used for cutting costs. The second thing is that choice and flexibility matter. I mean, even within our own data centers, where in theory we could run in a completely homogeneous manner, we wanted to be sure that we had the choice to pick from multiple vendors. And as customers, we wanted to make sure that those kinds of choices are available to you as well. That you're not locked into one particular vendor's proprietary offerings, that you have the ability to plug and play across multiple offerings to the extent possible. And flexibility, so that you have the choice in deploying workloads in the way it makes sense to you. If you want to have a deployment where you have a web front end hosted in a public cloud, but your data you want to keep secured within your on-premise private cloud, we want to make sure that that capability exists to make that happen. And finally, that agility and automation are key. And the idea here is that you want to move away, especially at scale, from managing your network at a, let's call it a per device, per port level. You want to have higher level constructs that you can control the network based off of. You want to be able to say, okay, I want to apply a policy that maps to a certain workload that I have, independent of the number of machines or network that workload is connected on. That's the level of abstraction that the data centers want to operate on, not at a per device, per port management basis. And so these were the learnings that informed what are the kind of investments we are going to be making going forward to enable the Cloud OS vision. So towards this end, we made three broad set of investments. The first is around cloud scale performance and diagnosability. How can you get the kind of scale that a cloud environment demands while having diagnostics capabilities to be able to troubleshoot problems quickly when they happen? A comprehensive SDN story. First off, SDN has a lot of buzz about it, but not everyone actually, sometimes even I get confused. What are people talking about when they say SDN in the first place? So we extended the SDN story that we started in 2012 with a range of enhancements in box and a great set of partnerships with the ecosystem. And finally, we have a set of core infrastructure enhancements to cloud optimize what we have already built. So what I'm going to do now is I'm going to start diving into each one of these broad areas. So the first is cloud scale performance and diagnosability. And again, the key goals here are to maximize ROI for the investment that you have made on existing resources that you already have and at cloud scale. Okay? So towards that end, I'm now going to start going down into a set of feature investments that we have made. This is at the overview level, but if you have questions at the end of the talk, I'll be happy to take them. The first is virtual RSS or VRSS. How many of you are familiar with RSS or receive side scaling? RSS is a technology that fundamentally allows you to spread processing of network traffic across multiple cores, which allows you to fully utilize the capabilities, the fully maximize throughput of the underlying NIC. But RSS is turned off in a virtualized environment. That doesn't help our cloud scenario. It's great for physical machines. How many of you have heard of VMQ? Fantastic. VMQ or virtual machine queue says that I'm going to take a VM and I'm going to affinitize it to a core. Okay, so now if I have multiple VMs, let's say I have 5 VMs and I have 4 cores or something along those lines, each VM effectively can get a core for its own processing, which is a good thing. You eliminate the contention and you're utilizing the system. But if you have a VM that has a need to use more than one core, because it is, that it just generates that much traffic, or it's compute intensive because it's maybe doing some encryption, then VMQ is not necessarily helping you. How many of you have heard about SRIOV? Fantastic. IOV is a technology that lets you bypass the entire stack and go straight to the underlying NIC. It even works with RSS. So you get the kind of spreading you want. But the challenge with SRIOV is that it is a special purpose NIC. It is not a commodity NIC that you can get. And the second problem is that SRIOV, well, it bypasses the entire stack. It bypasses the switch, which means that any ACLs or any settings, access control lists or ACLs that you have set on your switch are going to get completely bypassed. So IOV is well designed for the scenario where you have a set of trusted VMs that you want to be running. So all these technologies solve a set of problems, but if I am a tenant who has a large VM who wants to be able to use multiple cores, there isn't a good way of being able to get that. So with virtual RSS, we do 2 things. The first thing is we use VMQ, and now as traffic is coming in, the processor that is affinitized to the VM is going to get that traffic, and that's in the host. But if the traffic becomes too much, we will overflow onto multiple cores as necessary. So the host automatically starts scaling. In addition, we compute an RSS hash so that the VM now, when the packet makes its way up to the VM and the VM has to do some processing, we can now pick amongst multiple cores in exactly the same way RSS does today. So with virtual RSS, you now have the ability to spread in the VM, get multiple cores in the VM, and get multiple cores in the host as well, thereby being able to drive these big workloads that are traditionally hard to virtualize. You'll find that I have these silly little poems, so to speak, that kind of explain the gist of what the feature is. It's kind of inspired by my very young kids who I was doing poems with recently, and the kind of poems they create are, bear me for a second, I have a bear, it's a lot of fun, but they weigh a ton. That's the kind of poetry they're creating. And so that's the kind of poetry you're going to see here. But the idea is it explains what the gist of the feature is. You can spread in the VM, spread in the host, maximize throughput on existing hardware, on your existing resources. That's virtual RSS. The next is NIC teaming. As many of you have said, you're quite familiar with it. And the way NIC teaming works is it'll affinitize a VM or a flow to a particular NIC, right? So if I have a lot of flows that I'm generating, they can generally get load balanced reasonably well. If I have a lot of VMs, a lot of flows, you have the ability to maximize utilization of the underlying team. But if I don't have a lot of VMs, I don't have a lot of flows. Let's say I have one VM that has one large flow. Because the algorithm for NIC teaming affinitizes a flow to a particular NIC, you can have flows that are not getting distributed across multiple NICs, even though you have capacity available. Okay? So you have a big flow, that flow is affinitized to a NIC, there's lots of NICs, all that capacity is not getting used. Okay? So in the 2012 R2 timeframe, we invented a new mode called the dynamic mode. And in dynamic mode, what we do is we break up a flow, and a flow is simply a TCP connection. Think of the tuple IP port. We break up a flow into chunks based on natural gaps that appear in the stream, in the TCP stream itself. There are natural gaps in a TCP stream. We break it up into chunks, what we call flowlets. And we balance these flowlets now across multiple NICs instead of balancing only on the flow, which means that you're again being able to optimize utilization of the underlying NIC team. And once again, this works on your existing NIC teams that you have today. No modifications, no new hardware needed at all. Okay? So that's NIC teaming, dynamic NIC teaming that we introduced. So these were two performance features we introduced in Windows Server 2012 R2 that help maximize on the investment in hardware that you already have in place, okay, by just changes in software only. And so if you look at a visual of how NIC teaming works, in the 2012 R2 timeframe, you will find that the middle NIC, there are 3 flows I think, the middle NIC is going to get used more than the other NICs do, simply because of the way balancing works. So you have unused capacity on the other NICs that is getting wasted. But if you look at 2012 R2, it's a lot more dynamic because we're breaking it up into these flowlets and we dynamically balance across all the NICs based on these flowlets instead of the entire flow boundary itself. Okay? ACLs. How many folks are familiar with ACLs that we had in the Hyper-V switch? Many of you. So in the 2012 timeframe, we had fairly basic ACLs, useful ACLs, but basic. We allowed for being able to allow or block based on the VM, on the IP address only. That was the granularity that we supported. In the 2012 R2 timeframe, we now support being able to set these ACLs based on both IP and port, the whole tuple again. So now you can allow or block access not just to the VM, you can allow or block access to a workload running in the VM. So you can say that I want to allow HTTP traffic to flow through, but I don't want to allow RDP traffic to flow in. You now have the granularity to be able to set things like that. And even better, we made it stateful. We allow for setting stateful rules, which means that you now have the ability to, once you call a rule stateful, if a VM creates a connection outbound, the associated inbound rule will automatically get created for you. Okay? And we'll have a demo on all of this stuff. So that's kind of what we did with ACLs in the 2012 R2 timeframe. It's basically saying that we're going to extend a useful feature that we have to go from the VM to actually moving to being able to set rules on individual workloads and make it stateful as well. The next feature I'll talk about is remote live monitoring. So one of the things we learned in running Azure is that diagnostics matter a lot. And I mean, I'm sure all of you know this inside out. But I guess living on the product team, it's easy for me to build features, but I don't always appreciate just how hard it can be to diagnose features when problems occur. And with Azure, we got first-hand experience. I mean, we hear it from you. With Azure, we got first-hand experience. Because very often what happens is a trouble ticket gets opened, and the indicator is networking. It looks like there's a problem in networking. The server is not sending traffic back when a client is sending in, when client requests are flowing in, I'm not getting anything back from that server. So typically we use a variety of tools, and that's okay, that still stays, to try to diagnose the problem. But in the end, you want to look at a packet capture on that machine. You want to go and say, okay, show me a netmon trace, or your favorite tool. Show me a trace so that I can look at these packets flowing on the network and see, well, is the problem really on the host or is the problem on the network? And what the problem in 2012 is that this is cumbersome to do, because you have to log on to that machine generally, you have to start up these traces, then you have to take those traces, give them to someone who can start then looking at them. In the 2012 R2 timeframe, we allow all of this to be done remotely. So I can remotely capture packets from a server We use WMI to set the server up so that it starts remoting a packet stream back to the requester, all admin privileges only, obviously. You start remoting packets back to the requester in near real time. So it's not real time. It's not like if there's this, 10 gig of traffic flowing here is not going to translate to instant results on the machine, but it's still in the order of seconds. So it's still pretty quick. But now you can see all of this remotely without having to go and log on to each and every machine to do so. And even better, we now also aggregate ETW events along with it. Because typically you'll see a network pattern, you'll look at an ETW event, and you'll try to correlate across the two and see, oh, okay, that's where the problem is. We now have a single GUI, or graphical user interface experience, around being able to aggregate across a packet stream and the ETW events. This tool is the next generation of Netmon called Message Analyzer, and it aggregates across both a remoted packet capture stream and ETW events. And so fundamentally, this says that you have the tools to be able to diagnose problems quicker. Okay, so it does not say that we will tell you that's where the problem is. That still requires expertise, but at least you have the tools that let you get the information quickly so that you can diagnose problems faster. There are other tools we also built that we will try and demo next, a tool that we call Test Net Connection. Typically, when you want to diagnose network problems, the first thing at least I do is I run ping. Can I ping that server? Next, I run traceroute. Where in the path is this packet actually dropping? I do a DNS lookup. Can I resolve that actual name? I have a set of steps that I do, but all these tools are disparate. They're all separate tools that you have to run and correlate. In Windows Server 2012 R2, we have aggregated these tools together into one tool that we call Test Net Connection, a PowerShell script that hopefully will help you diagnose problems a lot faster, and we'll try to demo that as well. So next up, I'm going to invite Charlie Wen, a program manager, to show the cloud performance scalability aspects that I had just talked about. Charlie.
Right. Check. All right, can you hear me? Is the microphone? Okay, good. So my name is Charlie Wen. I'm a program manager from core networking team, and let me just log on to the machine first. All right. So the first demo I'm going to do is VRSS, virtual receive side spreading. So the demo is very simple. I have two machines, have a sender and have a receiver. Now, to give you draw some contrast between without VRSS and VRSS, I'm going to do a demo to show the behavior on 2012. So you will see what happens, what we will get on 2012. So I'm going to send traffic on this send machine. I'm going to move back to the receiver. All right. So I want you to pay attention to this this number. So basically, that's the throughput you can get to this VM. Now, if you have a very network-intensive workload, you will see you are limited to this throughput, and the reason is actually you are bound to one CPU. It's not just bound on the virtual processor in the VM, but also bound on the virtual processor on the host. Remember, Ravi actually mentioned the traffic comes in, the host has to decide whether to send the VM, right? And because you have so much traffic, the traffic is always sent on one processor. That processor, the cycles of that processor limit your throughput. So the next thing I'm going to do is I'm going to enable VRSS. So all you need to do is log into the VM and run the PowerShell enable net adapter ISS. That's all you need to do. Okay? So I'm going to run the same test again. I'm going to actually give it a range a little bit longer so you can see the effect. The tool we use is traffic generator tool, and it's called the NTTCP. It's available on TechEd, and you can download and simulate. So these are all live demos. Hopefully they work. Okay. Okay. All right. I seem to have some problem with this run. We have some traffic spreading, but the throughput is actually not what we expected. So if you trust me, it worked minutes before this talk, but we'll see. We'll investigate what's the reason. But the goal is simple. The goal is actually when you enable VRSS, we want to increase the throughput, and we want to better utilize the resource, CPU resource. That's the goal. Okay, I'm going to move on to the second demo. The second demo is NIC teaming. So I saw many people are familiar with this NIC teaming solution. It's a built-in Windows Server 2012. Now, I want to give a quick just a description of this demo based on some previous feedback. So I have a setup. The setup actually has a 4 1 gig NIC, okay, and also have 4 VMs, and 3 of them are actually doing the transactional transactions. Now, as you know, like a transaction, basically, I send some traffic and receive some traffic, right? And then I have a 4th VM as a backup server. It's just going to receive traffic. So in summary, I have a 4x1 team, and I have 4 VMs. 3 are receiving, 3 are sending traffic, and the 4 of them are all receiving traffic. Now, first, we are running this load balancing mode. It's called address hashing. Now, we know like address hashing basically does the tuple, we do the hashing based on the 5 tuple information. And what you can see is on the right-hand side, you see 4 bars. Basically, there's 4 NICs, right? So we actually do the distribution on the send side. We do the distribution and send the traffic on these 4 NICs. Now, on the far left, you see actually this is the receiving bar. All traffic are received on a single NIC. That's actually the limitation of the address hashing. That's what address hashing gives you. And because this is all the received traffic is bound on one single NIC, that also affects the transmission side. Right? You can see the transmission on each transmission side, the NIC, the throughput on the transmission side is very low. Right? The sum of them actually is bound to is to 1 gig. It's about 1 gig. So the next thing I'm going to do is I'm going to change the hashing mode to Hyper-V. So this is actually the default mode in Windows Server 2012. So this mode, actually Ravi mentioned earlier, this mode allows you to affinitize a VM to a NIC, a team member. Now remember I mentioned there's there's only 3 VMs sending traffic, right? So that's why you can see on the right 4 bars, only 3 of them actually are high because only 3 of the VMs are sending traffic. But on the receiving side, we have 4 VMs, so they are all receiving traffic. So Hyper-V mode allows you to affinitize a VM to a team member, but it actually doesn't utilize all of the resources available. So that's why we actually introduce dynamic mode. So once you enable this dynamic mode, you will see actually on both send side and receive side, we actually do the spreading across the team members. Right? So this is a NIC team. We learned from customers. NIC team is used to create this converged fabric. Right? You have a Hyper-V server. You have a 2x10 NIC. How do you actually you converge all the workload on this? So with this new mode, it will give you better utilization of the resource, or your existing resources. All right. So the next one I'm going to do is extended Port Echo. So for this demo, again, I have two VMs. One is just a web server, and one is a web client. So this is a web server, just a very simple web server, basic setup. Now this is a client. If I open a web page, and I cannot log on to the web server because that's by design. Because what you have is, you can see, I have filters actually configured on both directions for this VM. So now if you are a service provider, basically think about this scenario. You actually onboard a tenant VM, right? Basically, you actually want to protect your infrastructure, right? That's what Azure does, is actually make sure that the tenant VM can only talk to the resources or the destination it is allowed to. So basically, you have this default filter to reject all the traffic. So what I'm going to do now is I'm going to just add the echo to allow this web client to connect to this web server. Right. So once I do that, if I refresh the web page, now I can connect to the web server. Now I want to go back to the script just for a minute, and you can see here I create a stateful rule. So what it does is actually the rule is created on the outbound connection. Because what we learned is when you specify echo, right, you actually, many times you can only do the classification in one direction. Right. But how do you actually, if you create a stateless, you have to create, if you want to apply the same rule to the return traffic, you have to find a way to, you have to create a corresponding filter, but sometimes it's just not easy to create. So that's why we created the stateful. It allows it will examine the traffic in both directions. So if you get this command again, if you run the echo, we have create an outbound stateful loop. So that's the example demo of extended Port Echo. So the next one I'm going to do is, well, since I'm here, I'm going to do the TNC. Ravi mentioned that there's a test net connection. This is like we combine a number of diagnostics tools together, like a ping, an NS lookup together. So what you can see here is, let me clear this screen. You run this command test net connection, and go to our favorite website, and that's give you the information. It gives you, the IP address. And information is like this is you will never get from the existing tool, like which outgoing interface you are using. So if you have a multi-home VM or multi-home machine, you want to know, which the traffic goes out to which interface, that gives you that kind of information. Now, ping only allows you to, it's kind of a layer 3. There's the IP address ping. With this tool, you can ping, you can do sometimes people call the layer 4, TCP ping. So you can ping the web server of Facebook. We ping the web server as a ping the remote port 80. Right? That's the information. You can do the layer 4 ping. Now, you can get more information with this flag. Okay, so this use this flag and specify the detail. It gives you just additional information. So like give you not only the IPv4 and IPv6 information here. And finally, we really put everything together in this tool. You can also do trace route with this tool. So it takes some time to run, and you can see the TTL here. And eventually, it will give you a number of steps, number of hops this tool go through before it reach Facebook.com. So that's TNC. Actually, I forgot to mention, actually, you can see we actually created the alias for it. It's simply TNC, test network connection. All right, so the last demo I'm going to do for the performance and diagnostics is remote packet capture Okay, let me log in. All right, so what you are seeing here is actually before the demo, before the presentation, I already did a packet capture. So this is message analyzer is our next generation of Nemmon. So Nemmon allows you to capture packets and events, and we are doing this with this message analyzer. And you can see we are actually capturing packets. If you go to here, File, Capture, and what you can see here is we are not capturing packets on the local machine. We actually log on to a remote machine called the Next server desk. We actually remote logging to use RPC and get the information there and do the capture. So let me do a live demo. Okay, go back and start. Okay, just recap. The scenarios for this tool is, we already get a lot of traffic. That's good. So the scenario is, if you want to, two scenarios we are trying to focus. One is, once you have a problem, you want to identify the problem, you can try to capture the packets and then move the file to some machine to do some analysis. And the tool will capture all the events and the packets. The second scenario is you want to actively monitor something going on in your infrastructure, in your data center. You can use the same tool to do it. So I didn't pay attention. Did I refresh or it's a recapture? Okay. So, all right. So I'll just stop here. So that's my demo. Back to Ravi.
Thank you, Charlie. That was, am I live? Am I? Okay. So that was 5 demos he did. 4 worked, which I think is pretty good. And in virtual RSS, I think the thing that you saw is that you saw the spreading. You saw that the traffic was no longer being processed by a single core in the host and the VM. You saw it spreading. And spreading fundamentally automatically means that you are going to see throughput rise, but you didn't see it today. So again, with this capability, you get to maximize ROI on the investment you have already made on existing resources and being able to do all of this at cloud scale. So that's cloud scale performance, diagnosability, and security. The next area I'm going to talk about is a comprehensive SDN story. Now, SDN is a buzzword, meaning once you have a buzzword, you can define it any way you like. And we see that in the industry. Everyone is defining it in the way they like it. So I'm going to do the same thing. But the motivation for this really is that customers want agility in their networks. I mean, to the extent that you have a workload that you have deployed on your network, and you never change that again. Existing mechanisms like VLANs, for instance, work great for that. There's no problem with VLANs, actually, if you have a fairly static network. But if you have these networks or you have a business where things change, you have a new policy that has to get applied. You have a new tenant that is coming in. You have a new workload that requires isolation. You have a VM that's getting migrated. Then the existing traditional mechanisms which use VLANs don't provide you with the flexibility necessary to easily accomplish those kinds of goals. Okay? So the promise with SDN is to say that I'm going to give you, the customer, higher level constructs that give you complete control over your entire network. You are the master. The network is going to respond to your demands. And there is a centralized mechanism or decentralized, depending on how you look at it, but there is a mechanism that lets you get an overall view of this network and be able to make changes on it. So that's the fundamental promise of SDN. That the networks of today are fairly inflexible, and you really, really want a mechanism that is going to give you the flexibility so that you can meet, the ever-changing business needs. The mechanism that we have in place is based on some key principles. The first is that it is open, extensible, and standards-based. Okay, so we have an open model. We work with a lot of wonderful partners to extend this model, and it is all standards-based. So we are not building something, so to say, proprietary here. It will work on your existing networks. Again, the theme that I've been trying to lay out throughout. Existing network. You do not have to overhaul your physical infrastructure to gain the benefits. And we have in-box solutions that can be supplemented with partners depending on your need as well. So the first question is, how do you get agility on top of a physical network infrastructure that is fairly inflexible? I mean, you have your switches and routers that are really laid out in the way they need to get laid out. Policies are applied so that traffic gets managed correctly. It is a fairly inflexible infrastructure. So the first question is, how do you get this? How can you get agility in networking if the network is actually not that agile? And so the first part of this is to take the policy edge of the network. So the policy edge of the network is the edge where you apply your network policies. To take that policy edge of the network, which is traditionally your physical switches, and move that to the virtual switches that are in the host. Okay? So move your policies from the physical network switches to the virtual network switches that are in the host. Okay, so that's the first step. That requires a fairly rich switch. You need a switch that can do all the kinds of things that you traditionally expect of your physical switches. Like VLANs, like QoS, like SLAs, like metering, like DHCP guards, and all kinds of capabilities you kind of expect to get from a physical switch. You need to get those same capabilities if the policy edge were to move into the host. In Windows Server 2012, we have a pretty rich switch. It provides all the kinds of core capabilities that you need, but even better, it is extensible. Not replaceable, extensible, because an ecosystem is not built by replacing pieces. You want this capability, then let me get rid of that capability. That's not how you build ecosystems. You want ecosystems to be extensible, where I can have an S-Flow plugin from one vendor, a firewall plugin from one vendor, and maybe forwarding capabilities coming from Microsoft Virtual Switch natively. The Hyper-V extensible switch in 2012 and in 2012 R2 provides you with this capability that provides you with these capabilities. Okay? And this is the foundation of SDN if you want to get those benefits on your existing network. So if you have an existing network that you want to get benefits of SDN on, the start point is your virtual switch. That's where you start. Now, once you have policies now that are configured on your virtual switch, whatever those policies may be, now you have much more flexibility because these switches are integrated with management tools. These switches are integrated into System Center VMM, and you can deploy these extensions, deploy these switches to all the hosts in one fell swoop. You don't have to go and manage on a per device, per port basis. So once you have the foundation laid out where you have the policies, the next step is you can now start overlaying customer requests on top of it. So one customer comes in and says, I need to lay out my topology with these IP addresses on top of the network you have. I want to provide this service to my customers. Okay? Now, another customer comes in and says, yeah, I have something fairly small, but it must be isolated from these other tenants. No cross-traffic contamination, please. So, with the switch in place, Hyper-V network virtualization is a technology. How many of you have heard of HNV or Hyper-V network virtualization? Okay, great. It's a technology that allows you to overlay customer networks on top of the existing physical infrastructure that you have in place. Customers can bring their own IP addresses, their own topologies, into, your IT cloud or into a public cloud, wherever the customer wants to go. And that same address space can get hosted on top of a physical multi-tenant infrastructure that the hoster is providing. So effectively, you have a customer address space, which is what the customer is, and you have a provider address space, which is the provider. Okay, that's kind of the model. And NVGRE is a standards-based protocol. I mean, GRE is a standard, and NVGRE uses that standard to basically allow encapsulating the customer packet within a hoster packet. Okay, so there is an outer header, which is the hoster address space, and there is an inner header, which is the customer address space. So the network infrastructure of the hoster simply routes based on the provider address space that is in place. And the tenant then gets the packet finally as it's supposed to and does whatever it does with it, not even knowing that it is hosted on top of a shared physical infrastructure. So you start with the switch. You now bring in Hyper-V network virtualization, which helps you build these overlays, these topologies that say that I want my VM in Azure to be the web front end. I want a SQL backend in my enterprise. I want to be able to enable that. Hyper-V network virtualization like techniques make that possible. Okay, they give you that kind of agility to respond to your customer's needs. So you have the switch. You move to HNV. Now, the feedback on HNV has been pretty promising, pretty good. I mean, a fairly influential blogger, you can look them up, said that NVGRE, which is the data plane used by Hyper-V network virtualization, is simply amazing because it has scaling characteristics that are much better than what other vendors have to offer today. Okay? I'm not going to go into a lot of details on this, but fundamentally, the scaling characteristics of HNV are significantly better than what is available in market today. So the question was, how could you take something that was simply amazing and make it better, right? And what we did is very simple. We said the promise of Hyper-V network virtualization is customers can bring their networks into the cloud. Well, we are going to say that customers can bring any of their topology into their cloud. So while earlier customers could bring in their IP addresses, now you can bring in not just your IP addresses, you can bring in your DHCP servers, you can bring in your host clusters, you can bring in your guest clusters, you can statically assign IP addresses to VMs, and everything, all that stuff just works with Hyper-V network virtualization, whereas it didn't in the 2012 timeframe. So we're taking what we had and fundamentally making it better. Okay? So that's the first thing. The second thing we're doing is that we are going to improve its performance because we want to maximize ROI on existing infrastructure you have. And so towards that end, there's two things we're doing. The first thing is we are integrating HNV with NIC teaming so that Hyper-V network virtualization now has the ability to use the full capacity of your NIC team, both inbound and outbound. The second thing we're doing is we are working closely with our partner ecosystem in building what are called task offload drivers. The way offloads typically work is you have something like large send offload. How many folks are familiar with LSO or large send offload? Some folks. The idea is an application has a large buffer that it wants to send. It wants to send a large packet because that's what it wants to do. But the network only takes these chunks. That's what the RFC is. It can only send these kinds of chunks. So you can either chunk in software or you can do the chunking in hardware on the NIC. And hardware has all the circuitry and the FPGAs and whatnot to actually make that process go really, really fast. So LSO is an example of an offload that you typically use with protocols like, with TCP, for instance, to offload the chunking of packets as they go on the network. Well, NVGRE is a new protocol, which means you don't automatically get that offload for free. So we are working with our partner ecosystem to provide LSO offloads for NVGRE-based packets as well. This virtualization protocol uses this underlying data plane called NVGRE. We are making that available through prominent partners, and I'll announce some of them in the SDN talk that we're doing on Friday. Okay, so we're allowing customers to get more of their topology into the cloud, we're driving up performance, and we are improving diagnosability of these HNV networks because they're new networks. They are new. So you need new kinds of tools that help you diagnose problems when they happen on this network. And we have a deep dive talk on HNV scheduled, I think, for Friday, where we'll be going into the details of how that exactly works. So that's HNV. So HNV, like I had said, does two things. It does one thing. It basically takes the customer address space and binds it to the underlying provider address space. So the customer may be operating in the 10.1 space. The hoster network might be in some 192 dot something space. NVGRE helps bind these two, loosely couples them together so that the underlying infrastructure knows how to route the packet and the customers don't know the difference. The problem was, in the 2012 timeframe, just going into software architecture for a second, we had layered HNV underneath the virtual switch. So you have the virtual switch on the top, you have VM sitting on top of it, and you have HNV sitting below it. So when the VM sends traffic, all the switch extensions that are sitting in the middle that want to do something with that traffic are seeing the customer address space because the customer address space is coming through. But the actual mapping to the provider address space happens below the switch in HNV. So all these extensions which want to provide value, like SFlow may want to provide information on the NVGRE packet, it can't do that. So in the 2012 timeframe, what we did is we moved HNV into the switch. Okay? The value of doing that now is that fundamentally all these extensions get to see both the customer address space and the provider address space. So if you have extensions now that want to block traffic, for instance, or do special things with traffic based on the hosted address space also, not just the customer address space, they have the ability to do that. One of the big things that came out of this is our work with Cisco around the Nexus 1000V, with the idea being now that you can have multiple virtualization protocols coexist at the same time. So again, when the spirit of us not trying to lock customers into one particular format or protocol or whatever it is, our switch now is uniquely positioned to actually support multiple network virtualization protocols at the same time if you use that vendor's switch extension. And I don't think others provide this capability, but maybe I'm wrong. Okay, hopefully that makes sense, that we moved HNV into the switch, so all the extensions become smarter, and at the same time, we introduced a hybrid forwarding approach where, one forwarding extension, like the Cisco extension, could say that I want to handle VXLAN traffic. So if a VM comes in on VXLAN, it handles that traffic. And if traffic is coming on HNV or Hyper-V network virtualization, we handle it. Very simple. Okay? So we started with the switch. Policies are applied on the switch. Policies include isolation policies that HNV requires. We built overlays on top of that allow customers to bring in a lot of their topology into the actual cloud itself. We enrich the ecosystem by allowing them now to see all the kinds of PACA address space that's in place. And then we say that in order to enable customers to bring in their entire topology into the cloud, there are other components that are also necessary. So if I want to enable a scenario where I have a VM sitting in my data center network or my cloud network using HNV, it wants to just go and talk to the internet. Well, there is no HNV on the internet. How do you communicate with it? You have a VM that says, I want to go and talk back to my SQL database that is sitting on-prem, within my private network. Well, you may not have H&V on that network. Or I have a VM that says, I want to go and talk to storage, within my data center network. But storage might be a physical resource and does not have H&V. You need a translator. You need something that's sitting in the middle that knows how to translate back and forth between the H&V traffic that is flowing and non-H&V traffic that needs to flow on the other side. And so in the 2012 R2 timeframe, we are providing inbox capabilities for site-to-site traffic, for NAT traffic or network address translation if you have VMs that want to talk to the internet, and for forwarding traffic for VMs that just want to go and communicate with another resource within the data center. Inbox components for the same. Now we could have done this in the way the other guys have done it. We could have done it by saying that, sure, just you want a gateway, spin up a VM for it. Just have a VM for that particular gateway. So now you have your tenant VMs. If the tenant VMs want to go and talk to the corporate network, I spin up a gateway VM for it, and now it talks to that gateway VM, which does the translation and puts you back to CorpNet. We could have done that. But if you have 10 tenants, you suddenly need 10 VMs. If you have 100 tenants, you need 100 VMs. And that goes against the spirit, again, talking with Azure, goes against the spirit of us trying to reduce your own CapEx and OpEx, because having 100 VMs isn't exactly free, as I'm sure some of you recognize. So instead, what we do is we introduced a notion of multi-tenancy. Everyone uses the term multi-tenancy, but we've introduced the term multi-tenancy in a way where a single VM can provide the isolation capabilities necessary within that VM itself to have multiple gateways for multiple customers hosted within the same VM itself. There was a lot of interesting engineering work involved in actually pulling that off, but now you can have, we said, one tenant, one VM? No. Instead, we'll say one VM up to 100 tenants, 100x magnitude improvement to allow for creating these scalable gateways in software that allow you to connect back to the resources that you have in mind. Now, this is supplemented by a great hardware ecosystem as well. And we will be talking about this hardware ecosystem in the SDN talk and in a talk that Charlie is doing on System Center VMM. I hope networking. I hope you're able to go for that too. Okay, and this gateway is highly available. So, even TCP connections, some of the TCP connections that you have ongoing, if one gateway were to crash, some of those TCP connections will actually fail over to the other gateway and the client won't know the difference. Okay, so I'll take questions at the end if that's okay. Okay, so we built in software gateways. So we started with the switch, we built in overlays, we made our extensions richer, so we built overlays, and then we allowed for complete topologies to be built around software on your existing infrastructure. And then we asked ourselves, okay, so now we think we have an SDN story and software that gives customers the kinds of benefits that they're hoping to get. The question was, can we do something if we had control of hardware as well? Let's say customer goes and says, yeah, I'm okay with buying new switches, no problem. I'm okay with installing new firmware on switches, no problem. Can we do something better? And so what we did is we said that we will have a consistent model for being able to manage switches within your network. And we work with the big name vendors, with Arista and Cisco, to do that. And the scenario we focused on was a common scenario. We said that you have VLANs that you typically set up on the switch, the physical switch. You have VLANs that you're setting up on the virtual switch. If these two can't communicate with each other, that's a problem, because traffic is not going to flow. So with PowerShell and with System Center VMM, we have an end-to-end flow, the beginnings of an end-to-end flow, this is early, of an end-to-end flow that now lets you diagnose basic issues end-to-end not just within the host or the tenant network, but within the physical infrastructure as well. Okay, and we use, again, standards-based schemas, DMTF standard schemas, to be able to do so. And all these switches, the switches basically that Arista will, I think they have announced, and Cisco basically will have support for OMI and a consistent model to be able to manage that on top of it. In addition, we have a logo program that will certify these devices as being OMI compliant. Okay? So, to summarize the SDN story, we started with the switch, we built overlays on top of it, we provided gateways to enable hybrid scenarios, and we now allow for managing your physical network as well. So the idea of getting flexibility in VM and topology placement, the idea of having automation where a central entity like System Center VMM has the ability to control your entire network, and control with the actual switch which enforces all these policies, we think, I'd love to hear from you, we think we have an inbox solution that now can deliver to the promise of getting the needed agility for your business. Okay. At this point, I'm going to invite Charlie back to do what I'll call a simple demo, because we have an SDN session in place, we have an H&V session in place. So in this demo, he'll show a point-to-site demo. He can talk about it. Charlie, thank you.
All right. So the demo is remote VPN, and some people call it point-to-site. The scenario is simple. If you are admin and you have your virtual network, you have a service hosted in Azure or some other service provider, you want to be able to log in and manage your virtual networks, manage your service. And we are demoing is we're going to demo this remote VPN through our built-in software gateway. So what we have here, you see here is I have two tenants. Right? On this one, if I try to log in, this one has a red tenant has a virtual network in some hosted cloud. If it tries to log in, it cannot. And you have to dial in. Right? Once you dial in, and he's able to log into the web server behind the built-in gateway. And similarly, you have another tenant, have another customer, and he can log into his web server. But I want you to pay attention to this IP address I used. Right? I used the same IP address. That's enabled by Hyper-V network virtualization. The service provider is using HMV, so the two tenants can bring its own IP for the web server, for their own web server, to the infrastructure, to the cloud. Now, what's interesting is in this demo, we are using our inbox gateway. And it's a multi-tenant, as Ravi mentioned, it's a multi-tenant gateway. We say the multi-tenant because these two tenants are logging to the same gateway. And we'll talk more in this afternoon's session, and we just dedicated that session for our inbox gateway. But just quickly, I want to show you, we introduced some new concept called compartment. And you can see on this VM, we have two compartments, one for each of these tenants. We can support many more, just to, so if you're a service provider, you don't have to spin off one VM for each tenant. And another thing I want to show you is these two VMs essentially are using two different technology to do the VPN. One actually uses IKE v2, and the other uses SSTP. So we support these two most popular VPN technology, so you can remote log into our inbox gateway. So I'll be happy to answer any questions if you have any. Back to Ravi.
Thank you, Charlie. So good to see that demo work too. That's the end of our demos. So again, just to wrap up on the SDN story, it's open, extensible, and standards-based. It works on your existing networks. and it is entirely in-box with great partner choice in case you want to use partners in your environment. Okay? So finally, I'm going to spend just a few minutes to talk about core infrastructure enhancements, specifically around IPAM. So IPAM, or IP Address Management, was a technology introduced in 2012 and provided great capabilities in being able to manage your IP addresses, DNS, device settings, so on and so forth. How many folks are familiar with IPAM in 2012? Wonderful. There is a complete session dedicated towards IPAM and core infrastructure on Friday afternoon, and there is a lab tomorrow afternoon as well that I would highly recommend you attend. In the 2012 R2 timeframe, IPAM, the main thing that we did was to cloud optimize it. And by that I mean three things. The first is that IPAM now has the ability to manage your tenant address space as well. So IPAM will give out address pools like it always does. SCVMM has the ability to manage tenant space within that address pool. And SCVMM now hooks back into IPAM and reports on IP address utilization so that IPAM UI can holistically report on it in one place. Okay, so IPAM can now streamline management of your overall fabric. The second thing with IPAM that we did is realizing that customers have a desire to deploy across multiple clouds. That meant that there are now going to be multiple cloud admins as well. And it is important to make sure that these cloud admins don't accidentally stomp on each other's changes that they might be making. So there's a lot of fine-grained security that we built into IPAM in 2012 R2 that customers will benefit from. And the third thing we built is that as you start moving towards cloud scale, the number of entries that you have to start maintaining around IPAM starts growing dramatically. So a local file or a local database is not exactly a scalable solution anymore. So we now move this into a SQL database and have rich PowerShell scripting to go with the same. So that's, in a nutshell, the kind of investments that we've made around IPAM, around core infrastructure, to cloud optimize it. And again, there's a session on Friday and a lab tomorrow where you can learn more. So I talked about three areas to close out. I talked about cloud performance and diagnosability, which was all about how can you maximize your ROI on the investment you've already made on existing infrastructure. With virtual RSS and NIC teaming, you get to maximally and optimally utilize the underlying NICs, the capacity of those NICs that you have in place. With testnet connection and remote packet capture, you have a unified diagnostic tool to be able to see whether there are problems occurring or not in one place, and if that fails, the ability to remotely capture packets, remotely capture events so that you can correlate and diagnose the problem as quickly as is possible. We've invested in an SDN solution which started in 2012 around making sure that you can build out the kinds of topologies that your business is demanding without being, without basically being a slave to the network infrastructure, the physical network infrastructure as it stands today. And if you have control over your network infrastructure, great, things can get even better, as I showed in how we now allow all the way from VMM to be able to control certain settings on the switch. And again, in the SDN talk, we'll go more into that. And finally, we made a set of core infrastructure enhancements that allow cloud optimization, especially with IPAM. So with that, I would like to say thank you very, very much for attending this early morning talk. And if you have any questions at all, please feel free to ask.